So once again, good morning, everyone. Good afternoon, depending on where you're joining us from the world. I would like to welcome everyone to Harmattan School. This is the 5th edition of the Harmattan School. And my name is Victor Ekpo. I'm Secretary General of the Nigerian Association of Medical Fields, and I'll be co-moderating today's session alongside Favor. Favor, please, can you say hi?
Good morning. I'm Favor Matayo, a medical physics intern at Aberdeen Royal Infirmary, Scotland. And I'm happy to join you today. I'll be hosting with Mr. Victor, just as I said earlier. Welcome once again to Harmattan School 5.0. The Harmattan School is a flagship academic and capacity building initiative of the Nigerian Association of Medical Physicists, designed to introduce undergraduate students to early career professionals to the exciting and impactful world of medical physics. Since its inception in 2021, the program has grown into a vibrant learning platform, attracting thousands of participants from across the world. And it is proudly endorsed by NAMP as part of its mission to promote education and professional development in medical physics, to inspire the next generation of medical physicists, and to bridge the gap between theoretical physics and clinical applications. So this year's theme, which is the physics of lasers, ultrasounds, and more, explores how the core principles of physics powers the modern technologies, from ultrasound to lasers to emerging innovations shaping the future of healthcare. You're welcome.
Okay, so thank you very much, Favor. And before we begin, we'd like to have a few quick reminders. We'd like to please remind everyone to keep the muted at all times, and because there are lots of people in the meeting, so it will be distracting if you're trying to speak above anyone else. You're also encouraged to drop your questions in the chat box during the lecture. Questions will be addressed during the Q&A session at the end of each lecture, and you're also you may also be invited to ask your question live. And before I forget, there might be a post-lecture quiz, and this contributes to your participation and certification. So, having said that, without any further ado, I'd like to introduce our program coordinator and president of the Nigerian Association of Medical Physicists, Dr. Iyobosa Blessing Owadie, for our opening remarks to the Harmattan School 5.0. Dr. Iyobosa, please.
Thank you. You just called all my names. Good morning, everyone. And thank you. Just like our moderators have said, we welcome you to the 5th edition. Last year, we couldn't hold the school, so it should have been the 6th one, but unfortunately, we couldn't hold the school last year. So I just want to say two things. On behalf of the Nigerian Association of Medical Physicists, we welcome you. This is not just another webinar or another summer school or there are lots of webinars and summer schools that are being held, all over the world by different societies. For us at NAMP, it's a strategy. We are trying to address the issue of shortage of medical physicists in the region, in Nigeria, in low and middle income countries, generally speaking. So the whole idea is to get, so the original targets of this school were undergraduate physics students, but over the years, we have seen that we have gathered interest from postgraduate students and even practicing medical physicists. But the whole idea is to get us to appreciate and see the different areas physics is applied in medicine. Beyond the regular, most people think of medical physics only in terms of radiation therapy, nuclear medicine, and diagnostic radiology, but there are several other areas physics can be applied in medicine, and that's what we've been trying to do every year, to introduce us to different areas of medical physics, with the aim that at the end, we will be interested in taking up careers in medical physics. So we are hoping that at the end of these 3 days, if you are not considering a career in medical physics, you will start to consider a career in medical physics. And then finally, if you noticed, so we have been partnering with IPEM, which is the Institute of Physics and Engineering in Medicine, for the past 6 years. And if you notice this year, most, if not all, our facilitators are from IPEM. And that's because the topics we are considering this year are very specialized courses, and we do not have experts in the country that can take those courses in the country and even around in West Africa. So this is also another big issue. So we're hoping that, like I said, at the end of these 3 days, we'll get medical physicists to start to look at areas like, lasers. Dr. Paul is going to tell us about that this morning. Robotics, prosthetics, rehabilitation, phototherapy, and ultrasound. These are areas you don't really find physicists in, especially in Nigeria. So hopefully that will be done. So once again, I just want to thank every one of us. Those are old and returning Harmattan School attendees, the new ones, and all our facilitators that will be joining us for these 3 days. Dr. Paul, Dr. Kuma, Dr. Keith, Professor Praminda, and Dr. Lucas, and other panelists that you will see along the way. So once again, thank you, and I hand over back to our wonderful moderators. Thank you.
Okay, thank you very much, Madam President. What a wonderful time to be alive. I think it's also my first time of hearing about lasers as something that medical physicists are interested in, and to find that they're even specialists in it and they call themselves medical physicists and not any other name. So it's a very fantastic thing that we are beginning to feel that. I'll just go through what the program for today is, because this is going to be very, very loaded couple of 3 days. And we're going to be having 3 lectures today. I'm sharing my screen now, if you can see it. We are going to be having 3 days of practical, life-changing medical field discussions for everyone. Today is mainly about lasers, and we have 3 lectures between the hours of 9 to 12 noon Nigerian time. And then tomorrow as well, the same thing. We're going to have the same different lectures on sound waves between 9 to 12. And then for what we call, for the day after tomorrow, in Nigeria, we call it next tomorrow. For next tomorrow, we'll also have 3 lectures on other aspects of physics that are very interesting and that I'm sure that everybody will benefit from. So without any further ado, the lectures are about to get started, and I'd like to invite my co-moderator to read the short bio of Dr. Paul Deacon-Smith, one of our Nigerian brothers by extension. Favor, please.
Thank you, sir. So today we'll be delving into lasers and clinical application of lasers, just as Mr. Victor has said earlier. And our first speaker for today is Dr. Paul Deacon-Smith, and he will be introducing us to the basic physics of lasers in the first session. Dr. Paul Deacon-Smith is the Principal Radiation Safety Officer, Laser Protection Advisor, and radiation instrument at Guy's and St. Thomas Hospital, London. He's in charge of training and issuing laser certificates at Guy's and St. Thomas Hospital, London. For any surgeon who is starting to use lasers for the first time, he has 20 years experience in training surgeons and medical staff on laser physics and safety. We're excited to learn from your expertise, sir. And so this is just to everybody. Please ensure your mics are muted all through the sessions. And if you have any questions along the line, you can just put them in the chat section and we'll answer them during the Q&A section. Dr. Paul, you may please begin when you're ready. Thank you very much.
Oh, great. Thank you very much. So just to introduce a little bit more. So I've been doing this for roughly coming up to 26 years now. So I've been in it a bit of a time, yeah. And I also used to respond to laser calls. So for example, if there was a problem with a patient on the bed, I'd go along and see if we could get the laser going, which would prevent them being sent home, because medicine is kind of funny field. You know, you patients coming with the hope of getting treated. So, you know, the one thing we have to try and do is to actually treat them. So we used to do that. We still do that, as a matter of fact. So I just wanted to make clear that when it comes to lasers in medicine, generally medical physics, we don't look to design a brand new laser. We can do that, but we work in conjunction with the universities, and most hospitals will have a university attached to them. So in our case, it's King's College London. And so if there's going to be any research on lasers, the school will do that part of the business and typically would work alongside clinicians. Primarily in medical physics, when you're dealing with lasers, what you're concerned about is the safety of lasers being used in the environment, okay? So you'll have your clinician or your operator who's a doctor, and they're going to use the laser. You may have some clinical nurses who are trained to use the lasers on, as you know, for treatment, particularly like in places like dermatology. But as a medical physicist, your job is to ensure that that equipment is working to the manufacturer's spec. And so what you'll do is that you'll do audits, annual audits. And in our case, we go a little bit further. We get involved with the purchasing to make sure like the laser is not some piece of rubbish that is going to break down. Yeah. So you're looking at it long term, what the costs are going to be, because there is a limited budget when it comes to equipment in any hospital. So you're kind of like a guard of the system when it comes to the equipment coming in and looking after it. Okay. So that's kind of like what it is. And my talks you'll see today is mainly explaining a little bit how the technology work. You garner more as you go along in time in the job. Yeah, you'll find yourself specializing depending on how they use the lasers. I'm fortunate to work in a center where there's a whole host of it. When I first started all them years ago, there was only 3 departments using it, which was dermatology, plastics, and theaters. Now lasers have just grown. It's like in everything. Even physiotherapists are using lasers, and it's really incredible to see how, as a tool, it's being maximized and finding its way, and there are different applications for it. Current research that I'm involved with the people from King's, they're now coming up with lasers where instead of having to take biopsies, they can use the laser itself to determine if there's tissue that is cancerous, for example, orally inside your mouth and things like that. So the field of lasers is growing and its uses are just expanding. It's unbelievable. Okay, so we're just going to go through the basic science to begin. And I think this is always good because this is part of the courses that we do. So we do courses for MSc. Sorry, I can hear some voices. Yeah. Yeah, so we do courses in the university for the scientific students coming through for medical physics, and typically this is the what would I say? This is basically the course material that we would use. We do not go into deep physics because as a medical physicist, you're not going to be required in your daily activity to be designing lasers, but you need to know how they work somewhat. And so this is basically extracts from the courses that we teach. And I hope that with the 3 of them today that you will get a really good idea of what we do. So I'll just continue. Okay, so these are learning objects. We get an idea of what a laser is. We'll have a look at the spectrum and essentially the things on this list, but we'll go through that because I think time is not on our side at the moment. Okay, so the laser is an acronym. It's just basically the letters for what it actually means, which is light amplification by stimulated emission of radiation, right? And it's a device that generates or amplifies coherent direction and monochromatic light via the process of stimulated emission. So if we look at what a light source is, for example, a bulb, the light emitted from a bulb is going in all directions, and generally they're not in phase. But with a laser, when the light that is manufactured are all in phase. So if you think of frequency where it's going up and down, all the light are going down, up and down in tandem with each other. And that's the one property that separates laser light from all other light, okay? Okay, so here's a spectrum. And I like showing the spectrum. So for example, are you able to see my mouse? Sorry.
Yes, we can.
Oh, brilliant. So this is the entire electromagnetic spectrum. And so if we look down here, there's radio. For those of us who can remember the days of radio, there's a lot of people who don't know what a radio is now because we have all these electronic devices. These are really long waves, and they will stretch for miles, you know, and so that's the bottom end, the weaker end of the electromagnetic spectrum. Then we go into microwaves. Microwaves are actually a point to note. Microwaves were the first laser. It was known as a maser. So the first laser ever made was a maser, and it was done with microwaves. And it was to test the theory that they could produce coherent light. And so microwaves are typical of your mobile phone, your microwave ovens, and things like that. Then we go up to infrared. Sorry. Infrared is like heaters. It's just beyond the visible light spectrum. It's a weaker end of the light spectrum. And you will see, for example, that we do use lasers within that part of the spectrum. Then we have visible light, which is typically what we see with our eyes. And there is a limit of visible light, but you'll find that most of the lasers that are used in medicine are visible. And then there is ultraviolet. Again, this is stretching at the other end of our visible spectrum, and we do lose a couple of lasers in that area. We'll come on to that later. And then after that, you get X-rays, which of course we use to see through the body because these rays are much more energetic, and as a result of that, their wavelengths are much smaller. And then finally, you get like gammas and cosmic. Gammas are typically used in radiotherapy. The beams that we use are on the order of anywhere from 8 MeV to 20 MeV machines. And when I say EV, that's how we measure the energy in a photon, which is what makes up the electromagnetic spectrum. They're all photons. And so typically it's 1 electron volt is 1 electron being pulled through 1 volt. And that's the energy that is involved here. And so when we speak about energy, that's kind of the reference that is used in science for that energy level. And then of course there's cosmic energy. Another part of my job is that we calibrate in a secondary standard lab within the hospital all radiation instruments belonging to the hospital, belonging to the school, and we also do it for many other hospitals. So it's a kind of unique lab in a way. There's not many in the country. And part of my discourse with respect to that, because we also teach that, is to let everybody know who are scared of radiation that your body, over the period of a year, every cell in your body would have been impacted by at least 1 cosmic ray. So we're constantly living in a radiation environment. And so radiation is not anything that is new to the human. And anyway, you can see my list below here, where we have ultraviolet, 200 to 400 nanometer, where we use a excimer laser, which is 308 nanometers. And the thing with that, which we'll come on to later, is they don't penetrate deeply, and that's very useful in terms of what we use it for in the hospital. Then you have your visible range, which is 400 to 700, your near infrared, 700 to 1400. And just to note that these are the things, these 2 ranges, this visible and near infrared, will make it to the back of your eye. So we consider them highly dangerous when it comes to work and require PPE to protect your eyes. And then after that, of course, you have your middle and your far infrared, but we'll touch on that. So how does it work? Well, this is originally a good description of what a laser is and how it works. Of course, now we have semiconductors and they're slightly different. They're produced by using PN junctions and having ways of getting the beam out. However, this is generally the system here that you see here is the standard for most lasers that you will come across. And so to explain it, you have a cavity, which is your cylinder that you can see here. There are 2 mirrors, 1 at each end. One is a completely 100% reflecting mirror. And on the other end, there's a partially transmitting mirror, which means it lets about 5% of the light within the cavity out. So lasers are highly inefficient. That's another thing to note. And then any material, you can literally lase any material, even the things that may not look transparent to us, may be transparent to the energy that is being produced. So we can use solid, liquid, gas, vapors. It's really amazing. And now they have things like plasma lasers. And basically, what you have is that you have your lasing material inside of this cavity. And then what we're going to do is that we're going to excite that material, and we're going to cause the electrons that are within that material to jump up many levels. And then when they collapse, that's how the light is produced. Now, once we do that to the material by exciting it, and the light is exiting the material, it will bounce around with these mirrors. In bouncing around, there's a little unique property that it does, which is to trigger. So each photon will trigger another photon from the material. So now you get two. And that's basically where the amplification occurs. And we'll talk about that later. So the other thing about our laser is we need a beam delivery system. So we'll have to attach something to it. We'll have a little look at that too. And your energy source. Energy sources can take two forms. It can be a huge flash lamp. Well, when I say huge, I mean very powerful. I mean, you wouldn't want to be in a room if that flash lamp went off. They're huge, bright, very bright. If you were to think of your mobile phone with a flash on it, and you were to put that up to your eye, you can imagine how blinding that would be. Well, that is exactly what would happen in the whole room with one of these flash lamps. And they're typically high voltage. They'll run anywhere between 1,000 volts and 5,000 volts, because you're going to dump a lot of energy across a gas, which is typically one of the rare gases, which is like argon or krypton, very neutral gases, so they won't react with materials around them. So you'll always have it as a constant gas. And that's the kind of materials that we will excite to produce the light, which is going to be the exciting energy for your lasing material. Okay, so that's typically how it works. Another thing that is particular about these mirrors in the laser is that they're not they're what we call first surface. They're not rear surface. So in the morning when you get up to go to work, what you'll do is you will look in the mirror to make sure that you're presentable to the world as far as you're concerned. But that mirror that you're looking in is a rear surface. That means the reflective part of that mirror is on the back part of the glass. It's not at the front. Well, we can't use that in lasers because then you get that anomaly that comes into play, which is the index of refraction. And that will change the beam's orientation. It won't be bouncing in the right way. And so what we do is the coating is on the front of the mirror. We use very special coatings, and we have to also put another coating which prevent that coating from oxidizing. And so that is why we call them first surface mirrors. The reflecting area is on the first surface of the glass and not on the back. Okay, so this is what it's about. It's about absorption, stimulation, and emission. So this is just a rough example of how the system works, where it absorbs energy and it goes up a level. From the inner core, it goes up. And then when it comes back down, it releases that energy. And then you can see as it goes along, it will stimulate an extra photon, so there becomes two. And that's kind of the amplification process. Just as a point, typically when we have systems that are working, the electron won't jump one level. What we'll do is that we'll jump one huge level, and when it comes back out, there'll be an almost immediate collapse to another level, which is not the ground state where it came from. And then there will be a further collapse of that electron back again down, which will be the lasing level, which is a much slower process than the first level. I know it's just how they work, and typically they're very well demonstrated in things like dye lasers. Okay, so we have the absorption, which is when the electron transits from the lower energy level to a higher one, which is what I was explaining. Then there's a spontaneous emission where the electron spontaneously emits a photon to transmit from a higher energy level to a lower one. And then you get your stimulated where the photons are bouncing around and stimulating other photons. And that is basically the explanation of a laser, roughly. So here's an example of the population inversion. So when we excite our electron and it goes up, it leaves the ground state and it goes into the excited state, which is this transition here. Okay, and then you can see what I was talking about, which is there's a fast reduction in levels by the electron, and then there's a slower collapse of the electron back to its original ground state. And this is where our lasing light is produced, not here, because this is just it collapsing back to a more reasonable state. And typically that reasonable state will be guaranteed by the environment because of the energy that you've put in. And so this is how it works. So we can use optical pumping, electrical pumping, we're using a voltage source and a huge electric field, or chemical pumping, which is a reaction. So with reactions, you're basically changing the state. But again, this whole process here is called pumping. So here I put in a picture of what a typical gas laser will look like. This is a helium neon laser. You'll typically see them, they're long little tubes. They're often used in the main laser as an aiming beam because the clinician who's doing treatment will like to know what area they're treating. And so with a lot of the lasers, there'll be a little red or green dot that comes out of the laser, which will be this laser, to point as to where the main laser is going to hit. We also use helium neon lasers as pumping lasers. So sometimes you have two lasers in one. One laser will be pumping another laser to produce a different laser mechanism, which is probably a really fast timed laser. So like things like pico lasers and femto lasers. So, but that's what we call mode. We'll get onto that. So you can see here where we're using the voltage is going through and we are exciting the gas to do the discharge. Our mirrors are at the end and then we produce the light. These here at the end are your mirrors, and that white light that you can see in the middle here, that very fine beam, is your lasing light. That is a light being produced in there, which will produce, which is actually the lasing occurring. And this metal thing is a shield. Here is an example of an electrode. So they're quite simple mechanisms when you look at them like this. But the whole idea of the electronics around it to guide it and to create it is quite complex. And like I said, highly inefficient. So some of our main lasers have cooling systems on them, which is like, if you look at it, it's equivalent to a car. They have radiators, they have waters running through, everything to keep it cool. So they're highly inefficient. Here's some examples of the mirrors. And these mirrors will be coated with material which will be tuned to the wavelength that that laser is made for. And so you can see here examples of the colors. And here we can see these are the lasing centers with the points where the light will exit. So it's not a lot. All this here will have reflections. And this is a point where in that non-100% mirror, they will be escaping through. So it's not a lot of the light that is allowed to leave. So having produced our laser, we need to deliver that light. And we have to get that light out somehow. So there's two main means of doing that. And so in our first instance, we can use fiber optics. And fiber optics are really clever stuff. I'm always intrigued by the fibers I come across, because when you look at them, they look like very fine plastic threads. I mean, you know, you can see here, you have your, like, typically what would be used for Christmas lights. But like with the ones that you're going to use, because we use fiber optics that go inside the patients, and they have to be small because, you know, you don't want to be creating large holes in patients. but the technique behind fibers is really clever. So they're not plastic. They're probably coated by plastic, but fiber optics are typically glass. So what you have is one glass inside the middle and another glass that wraps around that glass. And the whole idea is that these two glass have different index of refraction, okay? So they bend light in different ways. And in the case of the fiber, you choose a different kind of glass that is going to cause what we call total internal reflection. So as a result of the way the light is being bent in the glass, we get the light traveling all the way down the fiber till it comes to the end. When you're using some fiber lasers, for example, in dermatology, they have a few, which is the dye lasers. When you do a flash or press the button, there will be a slight flash along the fiber, but it won't be enough to cause a problem to users outside. Because not a lot of light escape, just some. But the main core and energy is transmitted down the fiber itself. So that's how they work, and it's really clever. And so that's one means of delivery. The other means of delivery is by an articulated arm. So for more powerful lasers, for example, your CO2 or some Q-switch lasers like the ND-YAG, used to be like, I think the first ones were the ruby lasers, but they're not used so much anymore, which was 694 nanometers in terms of wavelength. Excuse me. So what you have is a principle of basically like what you see in the submarine, where they put the thing up to look above the ocean. You have your mirrors inside your arm, and they're all first surface mirrors. And the beam will go along and is bounced around until it gets to the end. So that's typically what an articulated arm looks like. And at the end here, where you see the port, they will attach different handpieces, which might have lens to either give you a larger beam or a smaller beam, depending on the use. Okay, so alignment tends to be a problem. So one of the things that we do is, as part of our test, is we will stretch the arm, fire it onto a piece of paper, and we will have marked the point where the aiming beam is dead center to, or like a cross. And having fired a laser, we look for any difference, any wandering of the main beam away from what the aiming beam is showing. Now, we will normally use plus or minus 3 millimeters for that. Anything outside of that, we will want the engineer to come in and adjust the mirrors, because it means that the mirrors may have been misaligned because somebody's knocked the arm or something. So these are the things that we kind of look out for as physicists when we're checking the kit. So the properties of laser light. Okay, we're going to look at the prop now and see what separates it from regular light. So it's monochromatic, which means it's a single wavelength, okay? And that's why a laser will have a particular wavelength. For example, a CO2 laser will be 10,600 nanometers. We can use a dye laser, which might be 595 nanometers. You also get like lasers which are used both for eye and other uses, actually, which would be 532 nanometers. ND-YAG will be 1064 nanometers. So that's just examples of some of the laser light. However, nature is never kind. So however much you would like something to be ideal, it never is. So what you'll get is a very small spread of light that is being produced. We can never predict where an electron will start from and where it will end. And as a result, that's the kind of photons that it will produce. It won't be far off. So we're looking at probably just a few nanometers. But your main energy will be at the energy of that is specified by that laser. And here's an example of coherent, which is what I was talking about. They're all in phase. And so if we think about the electromagnetic waves in this way, then you can see what we mean. They're all in phase. They're not scattered in every direction. They tend to be true to polarization. So if you're using polarized sunglasses, for example, the laser light will go through in one way, and if you turn your glasses, it won't go through in the other way. And that's typically how the light behaves. It's all coherent and operated in the same mode. It's highly directional, and that's something about lasers. So one of the lasers we have, for example, is CO2. That will go, because we're right by the River Thames, it would literally go across the River Thames without much spreading. And the light will be in a nice narrow beam. And so you can imagine we can keep the power going for a great distance. There will be some spread on all lasers. And if you're using lasers from a fiber, that will spread really rapidly because it loses its coherence as it goes down the fiber. It typically comes out, and it comes out as an angular beam. And so generally all fiber lasers would have corrective optics. But when you're producing down an arm, it will be much more directional and in a narrow beam. So the other thing now is we've produced the light, we're delivering it down our source of delivery, which is the beam, which is the articulated arm or fiber. But we need to know how we're delivering that laser. And so the other means of delivering that laser, we want to know, because we need to know how much light we're going to use in a treatment. And so we look at it in this way. We have a continuous wave, which is if you press your handpiece or your foot pedal, the beam will just stay on and it will just keep going until you release. And so that's known as a continuous wave. There's also a pseudo continuous wave that is anything greater than a quarter of a second. And there's a reason for that. Pseudo continuous wave is only applicable to the visible range. And the reason for this is if somebody was to shine a light in your eyes, you would instantly respond, and that is called a blink reflex. And the typical average response when you look at someone who's young versus someone who's old, we take all those responses and we do the average, is a quarter of a second. So it would take a quarter of a second for you to totally close your eyelids in response to having light go into your eyes. So when we're doing safety measurements, we consider that as a continuous wave. It's almost as if somebody is shining a light at you constantly. And so when calculating out safety aspects and guards against that kind of light, we have to bear things like this in mind. This figure comes into it. Then you have your pulse. That's typically from 10 microseconds to 1 second. Most of the lasers you find in medicine are going to be within this range. They're going to be pulsed. And pulsed laser can occur because each laser light has to be produced by a pulse of energy in the cavity, or it's shuttered. So for example, gas lasers are more continuous lasers because it's just an electric field which is constantly on, which constantly excites the gas. And so the cavity is producing the light nonstop. That is typical of things like CO2s. If you wanted to turn it into a pulse laser, you have to introduce a shutter where you interrupt the beam. So you're going to chop the beam up into bits. And so shutters are used there. And so this is what you get in shuttered outputs. Never that ideal, of course, because nothing is ideal in nature. And then there is your Q switch. And this is another type of output. Q switch are very clever. The thing with Q switch is, if you think of the energy in this area, which is in your pulse here, what you're doing is instead of letting it out immediately so that you get this lasing effect over this period of time, what you do is that you keep the energy bouncing around in the cell, or you can keep all the electrons in a state where they're all standing up in their energy levels. And then at the last minute, you let them out. And that's why you get this shorter time period. Now, this is really good because what you're doing is the total average energy that is in here is also going to be expressed in this pulse. So we're looking at 4 to 40 nanoseconds. However, in our modern use, we no longer have these long times. What we are using is 4 nanoseconds, okay? And so you're talking about all the energy that will be delivered here is going to come out in a very short period of time. And that means your peak pulse is going to be much higher in amplitude than your regular pulse. And that's quite useful because explaining why Q-pulse is very good here. If you're using a laser on somebody's skin or in their eyes, you don't want to hang about for a long time. And the analogy I normally use is boiling a kettle. If you turn your kettle on to boil the water to make some tea, it takes a while. The energy that you put it in, if we assume a value and say 1 kilowatt, which is kind of low, but say your kettle is 1 kilowatt, it may take you a couple of minutes, 2 to 3 minutes before your kettle is even beginning to boil. And that would be in your pulse. It's delivering the same amount of energy over a period of time. Now, just imagine that you had a kettle where you could take all the energy that you were putting in over that period of time, and you were to suddenly put it into your kettle. Then what would happen is, literally, your water would immediately evaporate because it's so much energy that it just can't hold it. So it would just have this great big explosive evaporation. And that's the principle of our Q switch. So what we want to do, and the other thing about it is, heat is a time-related effect. So your water didn't boil instantly. It had to take, as it accumulates more and more energy, it gets hotter and hotter and hotter. So we know that heat is a time effect. However, in delivering this energy really quickly, we can do a lot of damage, highly explosive damage, without that major heating effect. And that's really good. So, for example, if we wanted to bore a hole, then we could bore a hole in a very small area and do the job really quickly. We're talking about nanoseconds. But at the same time, it wouldn't heat the tissue around it because it hasn't spent time enough for the heat to expand through the tissue. And so that's the beauty of a Q switch. So uses, for example, with Q switches are tattoo removals. When people have tattoos and we want to get rid of it, we literally want to go in and blow up the ink that is within the skin, but not heat the skin. Another good use is hair removal. And of course, a really good place to use it without causing tissue because damage, we don't want to damage the tissue, is your eye. So most eye lasers, when they're doing work, will be Q switched. They'll be really fast response lasers that will go in and do the work that the optician or the ophthalmologist needs to do without damaging the nice surrounding transparent media around it, the gel of your eye. And so that's the beauty of Q switches. So we'll move on. Okay, so here's the typical lasers found in medicine. We have gas lasers, CO2, which is a very popular workhorse. CO2s are fantastic in that they don't penetrate deep into the skin. They're very surface level working because it's a very long wavelength. And they can be collimated. So you can put lens into the beam and bring it down to a point in which it then becomes a fantastic knife. So surgeons can use CO2 to cut things. So like, for example, keloids on your back of your head and along your neck and places like that, typically we'd use a CO2. Because if you use a scalpel, there's a lot of blood and there's a lot of having to use a vacuum suction device to get rid of the blood as you're cutting away tissue. However, with a CO2, you can cut, because at the same time it's cutting, it's cauterizing the tissue, which leads to a lot less blood loss. And so that's the beauty of using a CO2. A very handy tool, can be used for so many things. And it can just take layers of skin. So you'll also find CO2s in beauty clinics, where they will use it like on your face and places like that, where you, what they call, do a facelift. So it will take off a layer of skin, which is very thin, leaving behind your new cells, which is coming out. So you can see why it would be popular in places like beauty clinics. And so, of course, you got helium, neon, and argon, and so on. You got your vapor, which is metal vapor, copper, gold, manganese, and so on. So you excite it by heating the metal to their vapor state and then applying high energy electrical pulses. We don't use that. There was one that came in on the trial, but I didn't feel like it was a safe enough instrument to have, because I just felt too many things could go wrong with it, so we didn't implement it. Then you have your liquid lasers. A lot of them lasers are liquid in places like dermatology. So these are organic dyes in solution, either water or solvents, and we excite them using very high-powered flash lamps. And it's basically the dye molecules that they're excited and give out their characteristic color, which is that wavelength that we want. Solid state, so your ND YAG, ruby and erbium YAG. So these are crystals or glass doped with rare earth and transition metals. They're very good. These are the lasers that actually scare me, to be honest. They look so simple. If you see the crystal core of it, there's some of them are just like 1 centimeter by 1 centimeter cubes, which you're going to excite. But these are the lasers that I always find that will put holes in things. So in my measuring instruments that I go along to check the output, with these guys, I'm always very careful. I always try to ensure that they are not at a point, you take them off axis, the beam off axis, so you try and get a bigger beam so that they don't bore holes in your measuring kit. And then, of course, you have your fiber. So these are rare earth elements which will be doped in your glass fiber. And by pumping light down these fibers, it excites these rare earth minerals here, and produce its own light, which is also transmitted along the fiber, and then you get it out. So they're typically excited by pumping using other diode lasers. And then, of course, your semiconductor lasers. These are growing in use because as a semiconductor technology gets better, they're now able to produce a lot more wavelengths. And so you're now getting blue wavelengths. I've seen wavelengths coming out which is bordering on the UV, and they're very stable. So once you start producing the light, you generally get continuous waves, and you can literally they just happen to be the most reliable lasers that I find around at the moment. They last long. We have them for years. They hardly go wrong, and I think they're really brilliant. And I really hope that they continue to expand this field. And then, of course, your Q switch, which is what we were talking about earlier. And so these are like basically the different types of laser you'll come across in a medical environment. So this is the end of this talk, and I just wanted to show you a picture of what a real laser looks like. So this is one of the guts of a laser which we took out of service, and I just wanted to show you. So in here is a laser cavity. So along there is a laser cavity, and along here will be the flash lamp, which is why you see these very powerful leads. And this one will be high voltage. This will typically be 2 to 5,000 volts that we will put in this flash lamp, which will excite this cavity, which will go along. And this is the pathway that you can see here of the laser, And here is your shutter mechanism. So this it's just an electronic shutter. You put the pulse across it, it will move out the way and turn off the beam. And here is a helium neon laser, and this is your aiming beam laser. So this aiming beam laser will always be on. It will bounce on this first surface mirror here, and there's a hole on the side here where it will go through and it will follow the pathway. And so what we'll use here is a glass that is basically a two-way mirror, and it'll be part of the system. It will go in and hit that mirror and come all the way through, and that beam will always be on, because in this shutter right here, let me just show you, in here is the lens, which acts also as a mirror. So this lens, while it's keeping the beam inside without letting it out, will allow the other light to pass through. So that's quite clever optics. So it allows one light through, but it doesn't allow another wavelength through. It will reflect that wavelength. And so that's just using clever optics to do that kind of thing. Here is an example of the cooling port. This is where the water will come in and then it will exit at another point. And that is, this whole system here will be flooded with water, and it will constantly be pumped around through and then enters out into a radiator where it will keep this whole system cool, because it does get hot, believe it or not. So this is a typical ND-YAG Q-switch laser core, okay? And this shutter system is part of the retarding system. So once this shutter system moves out the way, the light will escape. But once this stays in, this light, this lens here will keep the light that is bouncing around slightly off axis so that it cannot actually totally laze and lose its power. So what happens is the light is kept in a state where it's continually being excited, and its excitation is being kept up for a period after the flash lamp has gone off. And so that's typically what the guts of a laser can look like. Of course, you get different designs and so on. But generally, we do not get involved in that as medical physicists, because it's not our job to either try to fix them or to do anything like that, even though for years I've got involved with fixing them and looking after them. It's not typically the job of a medical physicist. And I also, as part of our safety lectures, ensure that we tell the staff they do not open the laser, because there's a huge risk of being either electrocuted or with that lamp going off in their eyes and them being blinded. And so that's it for this talk. I think we have 2 more to go. How do I get out of this?
Yes.
Okay.
Thank you very much, Dr. Paul Deacon-Smith. I hope I'm being heard.
Yes, I can hear you quite
lecture.
clearly.
Yeah, fantastic lecture. Looks like a very interesting part of physics to go into.
So I hope that, so
there
just
are
a
lots
point.
of questions.
Yes, I can take
box.
any question.
Yeah.
I hope you get to pass the.
Okay, great.
I hope you get to pass on the PDFs to the
there
people.
are lots of questions in the chat box.
Okay, let me find the chat box. Okay, cool. So.
Yes, we can do that. If that's fine by you.
Somebody has their hand up?
Yeah.
Please, go ahead.
If we can send it to us via email, we'll send it to all the registrants.
You're breaking up. You're breaking up.
After the lecture. Okay. Favor, I believe you were taking notes of some questions.
Thank you so much, Mr. Victor. Can everybody hear me clearly, please?
Okay.
Yes.
Okay, thank you, Dr. Paul, once again.
Go ahead, Favor. Please read out the questions in the chat box.
All right. So some of the questions are closely related to what our other two sessions would be on. The
Okay.
first question, yeah, one of the questions is related to how the lasers interact with the body and then the clinical applications. So I would suggest that we move to the next session and then we can answer these questions if the participants are still not fully and well understood on the questions. Would that be okay, Dr. Paul?
Oh, that's fine with me. We can do this anyway. I've put aside this day for you guys, so that's not a problem. I just wondered if there were any questions on the physics of the laser, or anything like that. It's fine if there's none. We can just move
There
on.
were some questions on the physics.
Okay. Well,
You can
well,
take
let's
those
let's
ones.
deal with them. We can go through it. I don't mind. It's easy to get on to the other talk, So
Okay, so I have a question here, and
yeah.
I'm just going to read it out. Under
Okay.
the ex on, this is a question by Evie Oyeto. I hope I'm pronouncing the name correctly. It says, under the examples of lasers, we have a semiconductor laser. Can you
Yes.
please explain how it works? A
Oh,
semiconductor laser.
sure. So if you did any kind of electronics or anything like that as part of your physics, you'll know that you have a PN junction. And so PN junctions are quite unique. So we use them to make diodes, things like that, which is why it's called a diode laser. Now, a diode is a semiconductor device which basically allows current to go one way but not back. And it does it by once it's using the idea of holes. So some of the materials will be lacking in electrons in its outer band, and some will have extras in their outer band. And by merging these two materials and having a little middle bit fusing those materials, what you get is a kind of transmission band where when the electrons are coming in, they will fill the holes in one direction and so prevent current going along. Or in the other direction, if you have the current going the other direction, they will just keep on going. Now, the beauty of that is they have energy levels in semiconductors. And so basically what you're taking advantage of is those energy levels, what we call band gaps. And with the band gaps, when we excite the band gap, your electron will go up to a certain level and then it will collapse. So typically diode lasers will use an electric field to do the excitement of the electron, which will jump up, and then when it collapses, it produces this light. So they will create small channels in that PN junction that will allow the light to escape. Because if you didn't, then the energy is kept inside the diode, which would be your typical diode, and would either escape as heat or as energy back to do more electricity, if you like. I think if you were to look on websites like Wikipedia and see how diode lasers work, they would give you a nice example, an indication of how the electron band gaps work. I think it's best when you look and you have the diagrams to see it, because I have the diagrams that I have here is a little bit too involved. I hope that answered the question. Another question?
Yes, sir. Thank you so much for the answer. Yes, so the next question I'm going to be asking is the same person actually asked about masers. You talked about masers being the
Yes,
first type of lasers that we
yes.
produced. Can you explain a little bit more about masers?
So the maser is typically that like the cavity I showed you. And what it was, instead of it being regular, ordinary visible light or infrared and so on, it's just further down the spectrum. And so it was microwaves. So microwaves was the first thing they used. It's amazing how materials work, which is something to. So my first point to answer the question is physics is not common sense. Okay, this is why to produce any real work in physics, you need to experiment, you need to measure, you need to actually do something to prove what physics is. It's not logical. Physics is not logical. That however much science appears to be logical, it's not. And so what it is that you're looking and peering into nature and determining what the rules are within nature. Yeah. And then having determined that, you can then go on to come up with models to do stuff and all the rest of it. And it's the same thing with like, for example, the production of light. It was an idea, but then they had to experiment. And in that case, they use microwaves, because microwaves are easier to produce in the materials they had. And so if what's a good way of saying it? So I'm always enamored by, if you hold up a lens, and the electromagnetic spectrum goes along, where it's small wavelengths, which are very powerful, up to long wavelengths that have hardly any energy in comparison. You would think that materials is built, and the way we see through glass is that the small wavelengths will go through the glass and the long wavelengths wouldn't. And that would be your common sense way of thinking about it. But it doesn't actually work that way. So, for example, one of the questions that I would ask some of the students in the science room is, if we had identical twins, they're both the same in everything, as far as we can tell, and one sat inside the house and was looking through a beautiful brand new glass at a garden, and one sat outside on the veranda looking at the same garden, the question is, do they see the same image? That is, do they see all the same colors? And most people would say yes, because when you look through the glass, you can see the colors. But the truth is, they don't. The one who is sitting behind the glass has lost some colors, and the one outside is getting all the colors. And that's the most amazing thing about material. So if one is to look at the spectrum of any glass, you'll see that it goes up, and it will allow through these whole wavelengths, and then it will fall down. And even in some cases, it might only lose 5% of some of the energy up there, but your eyes is going to get the 100%. And that's typically what happens with most materials. So there's materials that are, when we look at it, it looks as if no light will go through it, okay? And so for us, it's opaque, and no light will pass through it. So we think, this will never let anything through. But that material may be completely transparent to microwave, okay? Or to infrared. And so that's the most clever beauty of it. So in the first instance, when they made the laser, they used materials for microwave energy, which is a much lower energy than visible light. And their aim was to basically prove Einstein, what would you say, theory on how light behaves. So that, Einstein did a work where I think he got a Nobel Prize for that one. What it was is he shone light on a material of different wavelengths, and he had a means of seeing at what point he kicked an electron off. And so that particular electron that came off, they would determine, they call it the work function. And it was from that principle that they went on to start looking at what things can be done. But it was Einstein's work in the original beginning that triggered the idea that they could do something like this, and to discuss the idea of having light that was in phase with each other. And so it's a whole history behind that. But if one looks at a maser cell is exactly the same as a regular light cell, a laser cell. So its production is very similar.